Hello everyone, welcome to the mathematical session on foundations of algebraic structures and number theory. In today's discussion, we are going to discuss on the concept of Fermat's little theorem. So it is a very important theorem in congruence concept. So I could tell you like to the next level, that is after understanding the concept of Wilson's theorem, Fermat's little theorem, it will be very important theorem. It's a key fundamental theorem in cryptography as an application. So what Fermat's little theorem says is, if P is a prime number and A is a co-prime number to P, then you can say a p power minus 1 is congruent to so what I try to tell is, like, if you take integer, that is for example a power p minus 1, a power p is nothing but the prime number, so a power p minus 1 is congruent to 1 mod p. So a power p minus 1 is congruent to 1 mod p. So that 1 before mod it denotes the relatively prime concept. Okay, the p denotes the prime number, a denotes the co-prime, any integer. Okay, so this is the concept given by Fermat. So what he says is, suppose if there is an integer and there is a prime number, and if you want to talk about its congruence concept involved, so you can say a power p minus 1 is congruent to 1 mod p. Then if I want to explain more on Fermat's little theorem, it is more important when it's come to algebraic concepts, that is modular arithmetic concepts like exponentiation used in cryptography. For example, if you say I have a value a equal to 2 and p equal to 7, I could say 2 power 7 minus 1 is congruent to 1 mod 7, that is 2 power 6 is congruent to 1 mod 7, 2 power 6 is congruent to 1 mod 7. Then to talk more on this, its benefits, its applications and its efficiency, I would like to say that the proof of this theorem relies on the properties of modular arithmetic. It could be related something like how we connected with Wilson's theorem, and as an application, as I told, it is used in cryptography, especially in the RSA algorithm, where Wilson's theorem is used in testing. So the efficiency computes large power. It computes large power modulo of a prime number. Okay, large power. So very large powers. So very large power modulo prime number. Okay. So before going into Euler's theorem, I would like to say that if you are going to work with Fermat's little theorem, for example, we were telling, like, if you take a equal to 2, an integer a equal to 2, then 2 power, you take the prime number like 7. If you see the previous slide, a power 7, I told you, like, you can write 2 power 7 minus 1 is congruent to 1 mod 7. So what it means is, this concept can be applied in problems where you are connected with finding the reminders. So for example, if you say 25 power 1785 congruent to 2 mod 7, so if this is the case, how will you find the result? So it is 25 power, a big power, so it is a complex term. So even though it is a complex term, you can use Fermat's little theorem to simplify it. And also I could tell you, like, suppose if you want to solve a given congruence relation, for example, if you say 24x congruent to 11 mod 7 or 13 some kind, so if you want to solve that congruence relation, and if you want to find the x value, if you want to find the x value, even you can work it on, even you can use this Fermat's little theorem result, and you can apply what is a, what is p, you can reduce, and very well you know the congruence concept, that is a congruent b mod m is equivalent to a minus b by m. So you can even apply that, and you can find the reminders. So step by step you can understand what is the exact solution required. So that is how we have to work, so that you can very well simplify a complex situation, and you can solve to get the x terms. So this is the best benefit of Fermat's little theorem. Thank you for listening. Thank you.